going to focus on quantum engines, although everything I'm going to say can be applied to other types of quantum machines. So when one thinks about a quantum engine, what is usually thinking about, it's some kind of system working cyclically, which is weakly coupled to two infinitely large thermal reservoirs, one at a hotter temperature, one at a colder temperature. There's heat flowing, and work is being extracted. But there are a lot of hypotheses behind this, such as infinitely large thermal reservoirs with coupling. And if we relax some of these hypotheses, then some interesting stuff starts to appear, which are other types of resources which are not necessarily thermal. In particular, I want to talk about three types of resources. Athermality, which is the easiest one to understand, which is a displacement from thermal equilibrium, so non-thermal states, for instance, squeezed thermal states, and it can be shown that the efficiency of an engine can be improved if, for instance, you use a squeezed hot reservoir instead of a thermal hot reservoir. Another possible resource is strong coupling between your working system and your reservoirs. And there are some conflicting results. In some cases, strong coupling can be beneficial to the working of an engine. The power can be enhanced. And in other cases, the power can be diminished. But at least having strong coupling modifies the behavior of the engine. And then the star of the show is coherences and correlations in general. There are a lot of things that you can do with them. You can extract work from them, for instance. Then you can use them to reduce the dissipation through some specific thermodynamic process where dissipation is understood as entropy production. And also there are other interesting effects, such as that the heat flow can be reversed, meaning that you can make heat flow from a cold reservoir to a hot reservoir instead of the opposite, that is what we usually are used to. So if one thinks about, okay, what's the most general engine that I can think of by relaxing some of the usual assumptions, then it should be a machine that it's able to use both thermal and non-thermal resources to output work. And this is very similar, for instance, if you want to make a simple analogy, to a hybrid car engine, that it can use the energy stored in the fuel and the energy stored in the battery to produce work output, to make the engine, to make the car go. And this comes with another extra beneficial effect, such that, for instance, the power can be increased, the efficiency can be increased, there's less fuel consumption. So we want to study what would happen if we have this in the quantum realm. So if we can take advantage of these athermal resources and what they can do. And as soon as one thinks about this, a lot of questions start to emerge, which is first and foremost how we describe this type of system, which is very complicated in principle. And then if we have available both thermal and non-thermal resources, then where is the work that it's extracted coming from? Does it come from the thermal resources, like from heat flows between reservoirs and system? Or can it come from the athermal resources? The question basically is what are the athermal resources doing? Can we extract work from them, or they are reducing dissipation, for instance? Along with this, does the engine have different regimes of operation? Can I make the engine work using only thermal resources or only thermal resources if both are available? And the most interesting to me is, okay, can the performance of the engine be improved? Performance measured in terms of, for instance, power and efficiency. So to answer the first question, I won't go into technical details, but we use the framework of non-equilibrium quantum thermodynamics, where we basically extend known concepts of thermodynamics that we have some intuition on to the realm of non-equilibrium systems. And for that, we start with a very, very general Hamiltonian, which is composed of a part for the working substance. The working substance is there in green here. It can be basically anything with different couplings. We only ask that it's periodically driven. And then we have reservoirs, which can be as many as you want, and they don't necessarily need to be composed of infinitely many particles, as the usual assumptions. They can be finite-sized reservoirs or with a finite heat capacity. And then we have a set of interactions that are in principle time-dependent between the systems and the reservoirs, and we don't ask any hypothesis about this. So starting from this very general Hamiltonian, we can derive, not assume that they are valid, but rather derive a first and a second law of thermodynamics that takes into account all these non-equilibrium effects. In particular, I want you to focus your attention, for instance, the first law of thermodynamics that usually relates work and heat. Since we are in a non-equilibrium situation with finite systems, we also have to take into account the change of the energy of the working system, because it might not be in a cyclic state, and the change of the energy, and the energy stored in interactions between the system and the reservoirs. And then in the second law of thermodynamics that we write in a very familiar way, this is a Clausius statement of the second law of thermodynamics, but we have to be a bit careful there, because although this is the change of the entropy of the working system, this is the heat, and these are the effective temperatures, this is kind of an information theoretical generalization of the Clausius statement, because this is the von Neumann entropy, and it's not the thermodynamic entropy. So, but other than that, this is very similar to the Clausius statement, and on the right-hand side, we have an extra term that takes into account all these non-equilibrium effects that I was talking before. Basically, the creation and destruction of correlations and the displacements from equilibrium. So when the engine starts working, there are many, many things that happen in between, but between the beginning of the cycle and the end of a cycle of the engine, correlations can be either created, which is the regime we know as irreversible. For instance, you're losing energy creating correlations, or it can either be destroyed and you can make use of them for extracting work, for instance. And this also takes into account displacements from thermal equilibrium. So we are not assuming that the reservoirs are in a thermal equilibrium state. We are just using a thermal equilibrium state as a reference point from which we measure displacement from. So for the ones that work in quantum thermodynamics, this sigma is the non-equilibrium entropy production, which it's a mutual information, correlations, and relative entropy. And once you have a first and second law, and you're talking about engines, the first thing you want to do is to write an efficiency for the engine. The efficiency is usually defined as the work output divided by the energy that you need to run the engine. And with this, we obtain a completely general efficiency for basically any quantum engine that we can interpret each of these terms. So I would like you first to look inside the parentheses. So the efficiency of the engine is composed by these three terms. The first term is the usual thermal efficiency that one is used to when working with an thermal equilibrium, an engine in thermal equilibrium, which can be written in the simplest case as the energy that flows in plus the energy plus the heat that flows out divided by the heat that flows in. So if your engine is just a system working cyclically, weakly coupled to thermal equilibrium reservoirs, then this is the only term you will get, the thermal efficiency. Now, there's an extra term here, which is very interesting, which we call entropic resources, which is the relative entropy plus the displacements from equilibrium of the working system. So this term here takes into account all these non-equilibrium effects, which are creation and destruction of correlations and displacements from thermal equilibrium. All the interesting stuff is codified here. We also have this term that takes into account the interaction energy. And finally, everything here is multiplied by a number between 0 and 1, which quantifies where is the energy that is needed to run the engine coming from. The answer to this usually is it's coming from the hot reservoir, right? Heat flows from the hot reservoir to the system and then to the system to the cold reservoir. and work is extracted. But when your engine is not in an equilibrium state, then the energy that is needed to run the engine can come from other sources, not only the hot reservoir. Maybe you have many reservoirs and it's coming from different reservoirs, or from the energy of your working system, the internal energy, or maybe you're extracting work from the interaction energy. Many things can happen. Now, okay, we have a general formula for the efficiency, but the question is, can we gain something? What's the upper bound of this? And is it larger or smaller than Carnot? So the first term, the thermal efficiency, as I said before, this is the one you would obtain if your engine is working in equilibrium between thermal states. Then it's very straightforward to show that the first term is bounded by the usual Carnot bound, 1 minus the quotient between the minimum and maximum temperatures. But then this term that takes into account the correlations that are created or destroyed during the cycle, it's bounded by a positive quantity, which is the correlations that were available at the beginning of the cycle and how your states are displaced from thermal equilibrium. So basically, this takes into account all the non-thermal resources that you had available. So the engine works using the heat flow between reservoirs and using some other resources which are non-thermal in nature, that are entropic rather. And if you have these resources available at the beginning of the cycle, then this shows that your efficiency can be increased above the usual Carnot bound. Now, a lot of things could be said about that, but I think it's more illustrative to look at simulations. So what we did was we simulate a quantum engine, a full simulation, not an open quantum system simulation, but rather a full unitary simulation of the following system. We have 2 reservoirs, each one of them composed of 300 harmonic oscillators, so we have 600 harmonic oscillators in total. And we have 2 other harmonic oscillators that are playing the part of a working substance. And by moduling in time the coupling between these 2 harmonic oscillators, we can extract work from the system. Now, it is important to say that we start from a correlated initial state. So we take a correlated initial state between this part, so the cold reservoir and this oscillator, and then a correlated initial state between the hot reservoir and this oscillator. So we are inputting correlations as initial non-thermal resources, and also displacement from local thermal equilibrium states. So the first thing we do is, using the same initial state, we change different parameters of the engine, namely the couplings, to obtain sort of like a phase diagram of the engine and understand how the engine is working, if there are many different types or regimes of operation. And we can see that in this phase diagram, we have 2 very different regimes. Here, which is what mostly dominates the diagram in violet, which is a thermal regime, and here in orange, it's the thermal regime. So in most of the parameter space, the engine is extracting work from athermal resources, so from the correlations and displacement from equilibrium. And then in a small sector of the parameter space, the engine is working as one is used to, is extracting work from the heat flowing between the reservoirs. This is for the first cycle of the engine. So we start the engine, and we register how the engine is working. Now, what we are going to do is to take a point here and a point here and compare it and see how the engine works in these 2 different regimes. So first, in a thermal regime, we can see these 3 plots that describe and allow us to understand quantitatively how the engine is working. So the leftmost plot is the heat that is flowing between the systems and the reservoir and the work that is being extracted. So this is showing that the energy of the hot reservoir is decreasing, the energy of the cold reservoir is increasing, and work is being extracted. Therefore, the engine is working as one would expect. Heat is flowing from the hot reservoir to the system, and from the system to the cold reservoir. And now, these athermal resources being positive means that it's constantly creating correlations while it works. So the engine is kind of wasting energy in creating correlations and drifting away from local thermal equilibrium. The consequence of this is that the efficiency of the engine is always lower than the Carnot efficiency. Here, this red line is the Carnot efficiency, and this violet line is the efficiency of the engine computed per cycle. So the efficiency, in this case, is always lower than the Carnot efficiency and quickly converges to the Otto efficiency, which is the stationary efficiency of this type of engine. So this is the thermal regime. No surprises here. It's working as one would expect. Now let's go to the more interesting athermal regime. Now, let's focus first on the leftmost plot, which also indicates that the heat is flowing from the hot reservoir to the system and from the system to the cold reservoir. So the engine is working in a way we expect, nothing new there. But this quantity being negative means that correlations are not being created, but rather they are being destroyed. So the initial correlations, and maybe correlations that develop during the cycle, are then destroyed to enhance, I mean, not to, but the end result of destroying these correlations and that the fact that the systems get closer to thermal equilibrium, the end result of this is that the efficiency of the engine is increased here as one we could see. So this red line, again, or orange line, is a Carnot efficiency for the engine. And we can see that for the first almost 15 cycles, the efficiency of the engine is increased above the Carnot limit, and then it stabilizes again at the Otto efficiency. Now here, we are not breaking any second law or doing anything weird. This was kind of expected. If we have extra resources compared to a thermal case, so the Carnot bound is derived for a thermal engine working near equilibrium or near quasi-statically. If we have extra resources compared to the Carnot case, it might be expected that we can do more. And we can do more means that the energy can be improved, the efficiency, sorry, can be improved for some time until those resources are fully consumed. So the takeaway from this is that generic microscopic engines have two different regimes of operations. One in which they are mostly fueled by non-thermal resources, but what we call entropic resources by correlations. And the other one, which is the most common, is the ones that they are fueled by heat. In the athermal regime, since the engine is actively exploiting extra resources, we can achieve efficiencies above the usual Carnot bound. And also, these results can be extended to any type of thermodynamic machine, not only to engines. So once you have a first and second law in general, you can apply it to anything you want. Refrigerators, which are very interesting, and this is a work in progress yet, heat pumps, or even accelerators. And with that, I thank you for your attention, and I'm open to any questions.
Thank you. Thank you for your talk. So,
thank you for the interesting talk. I'm not sure you're aware, but in our work in 2023, we have proposed a generalized efficiency, and the additional term is indeed given by correlations. We showed that this leads to an efficiency that can be above the Carnot result, and that this is given by the fact that correlations are consumed. So could you maybe compare your result to ours, if you're aware of that?
Yes, sorry. I am. If I remember correctly, the extra term contains the mutual information, right?
It contains the mutual information, and it contains also the entropy production.
Yes. So our results are very much similar. This might be a bit more generalized because we don't use any specific model. But the extra term that is contained in the efficiency is given by this. So we also have the mutual information here. These are correlations between systems and reservoirs, and these are displacement from equilibrium. So our results are in accordance. Yes, exactly. Yes.
Yeah, hi. Thanks. So actually, I think this answered one of my questions, which was the correlations that you're talking about, it's between system and reservoir. It's not correlations in reference with some Hamiltonian inside the system.
Yes, indeed it is. We have all these types of correlations. So between system and reservoir, correlations in between the system, and then correlations between the different reservoirs. So all of them are taken into account, and all of them take part into modifying the performance of the engine.
I see, okay. And then just second small question. In the end, when you show the plots, it seems that the first law doesn't work. Like if I add the heat and the work, it doesn't sum to 0. So
exactly, because you also need to add these other resources. That's very good eye. Yes, the first law needs to be a bit generalized. It's not only the sum of the heat, but you also have another contributions. If you only want to talk about the energetic part, will be the change of the energy of the working substance, because it's not in a cyclic state necessarily. It's out of equilibrium. So you need to take into account that, and also the energy stored in the interactions. But they can be rewritten in terms of this term. So actually, if you add the heat and these terms with some factor, you obtain the work perfectly.
I see. And this second term, you did not split it into work and heat. You just say, now I also have these extra contribution that need to be added to the first law, and then everything works fine.
These thermal resources are exactly this.
Okay, I understand.
Yes.
Okay, thank you.
Thanks for the great talk. So I also have a quick question about your definition of efficiency that we just seen before. When you calculate the displacement from thermality, do you use the relative entropy of a thermality, so to say?
Yes. Yeah. Not the relative entropy of a thermality, the relative entropy between the state of your system and a thermal state, which can be divided as a thermality plus...
and you choose the thermal state, or you optimize for the closest thermal state according to... Because if you do like relative entropy of a thermality, usually you like pick, like you have to optimize, and it's an expensive task to do. So I was just wondering what's the approach for you guys?
So is your question what thermal state do we use?
Yeah.
Okay, great. So we use the thermal state with the local Hamiltonian of... So our big system is divided in many subsystems. So I'm talking about one subsystem in particular. We use the local Hamiltonian of that subsystem, and the temperature is the effective temperature that makes the mean energy match, the usual...
Okay, sweet.
The usual definition of effective temperature.
Yeah, which is like very simple to calculate, essentially. Awesome. And a quick follow-up. So I saw that you're calculating this efficiency at the level of the density operator. Have you ever thought about doing the same thing and entropy production rates at the level of the individual trajectories in a sort of stochastic wave function Monte Carlo approach?
I was thinking about that, and it would be very interesting, yes. We haven't done yet, but that's an idea in the back of my head.
Okay, cool, thank you.
Other question? Okay, so I have a question. In order to be sure that your efficiency is well defined, you have to prove that QI over sigma over Q should be always smaller than T cold over T hot. Can you prove this?
You mean?
No. Yes, this one. Yes, sure. Yes.
That this should be always?
Should be always smaller than the T minus over T max.
This should be smaller than this?
Yes.
Why?
Because otherwise the efficiency will be larger than 1.
No, you can prove that this whole thing is less than 1.
Okay.
This is,
so,
yeah.
Which is equivalent
okay.
Yeah.
Yeah, no, you're right. Sorry, I didn't see it, but yes, you're right.
Okay, sure.
Yeah, you can prove that this is always smaller than 1, yes.
Okay.